Alright, so for starters, we're going to finish section 10.1, which is infinite sequences. So where I ended last time, we showed that bounded sequences, relationships between bounded sequences and convergent sequences. So I showed that convergent sequences are bounded. But the converse is not true. Okay. So for example, the example that I showed in class, I said a and n was -1 to the n. So if you graph this guy, it keeps jumping back and forth between -1 and 1. Right? So it's certainly bounded. Right? It never goes above a certain value, it never goes below a certain value. But it's not convergent. Okay, it's not convergent because it never levels off to a limit. It just keeps jumping around. Okay, so when can we tell if a limit converges? So I'm going to give you a definition. An is increasing if a sub n is less than a sub n plus 1 for all n. Okay, this is the definition of increasing. And I think you can guess what decreasing in is. It's decreasing if a sub n is greater than a sub n plus 1 for all n. Okay. So you should think of a sequence that's increasing looks something like this. Because maybe this is A3, A4 is bigger. Right? A decreasing sequence would look something like this. Okay. Okay, so here's a theorem. Okay, before I give you the theorem, let me finish the definition. So I say an is monotonic if an is increasing or decreasing. Okay? So for example, this sequence up here is not monotonic. Okay? because it keeps jumping around. It doesn't always go down or always go up. Okay? Okay, so here's the theorem. If AN is bounded and monotonic, AN converges. Okay, so in other words, it has a limit. Okay? So rather than giving you a proof, let me just draw a picture. Let's draw a bounded monotonic sequence. Okay, if it's bounded, then there's some bound up here, so let's say that this is my bound. Okay, so the sequence can never get above that bound. Okay, the sequence is always below. That's what it means to be bounded. Now let's assume that it monotonically increases. So let's say that the sequence increases. Okay, so let's draw the sequence. It always has to increase. Okay. So you see that if it's never going to get above this bound, it has to get infinitely close. Okay? So this is going to be my limit. Okay, that's the idea. Now, if this is the lowest possible bound, this is going to be the limit, but maybe my bound is much higher than that. So the limit and the bound don't have to be equal. But if the bound is the lowest possible bound, then they are equal. So here's an example. Okay. Okay, so here's a sequence. And I'm wondering, does this converge? Does it have a limit? And what is that limit? Alright, so let's show that this guy, let's see if this guy increases or decreases. So let's list some elements. So let's say A1 is square root of 2 minus 1. A2 is square root of 3 minus square root of 2. A3 is 2, because the square root of 4 is 2, minus square root of 3. Okay, if you plot this, if you get a decimal approximation of these guys, here's A1, A2, A3 are going to be like here, here, and here. So it appears to be decreasing. But I'm not sure. How do we know if it's decreasing? Okay, to show that a function decreases, consider f of x is equal to square root of x plus 1 minus square root of x. Okay, to show that this function decreases, we need to show that the derivative is less than 0. So here's the idea. If my function looks like this, if it's decreasing, the derivative is the slope of the tangent line. So let's say that this is x. The derivative is the slope of the tangent line. So if the slope of the tangent line is negative, then the function decreases. So you just need to take the derivative of this. So the derivative is 1 over 2 root x plus 1 minus 1 over 2 root x. Okay, this number down here is always bigger than this. So when I divide by a bigger number, this guy's going to be smaller, and this guy is going to be bigger. Okay, if I subtract a bigger from smaller, I get something negative. So this guy is less than 0, so it decreases. Okay, also, you can see that a sub n is always bigger than 0. So a sub n is bounded. So if it always decreases and it's bounded below, then it must converge. So it converges because it is bounded and monotonic by this theorem. We can actually see what it converges to by doing a rewrite. So you can say an is equal to root n plus 1 minus root n. And you can multiply this by the conjugate. So you can multiply this by root n plus 1 plus root n over root n plus 1 plus root n. Okay, when you FOIL out the top, what you're going to get is 1. And on the bottom, you're going to have n plus 1 plus root n, and this guy goes to 0. So it converges, and it converges to 0.